welcome to Module 24 of AP Environmental Science. This module covers a lot of earth science information that you should have gotten in past science classes, but I'm just going to briefly touch on those points that should be reviewed and then go into a little bit more depth on the pieces that are actually applicable to the AP exam, so that way you know what is actually important in this module. First little bit is the timeline of the Earth and the geologic time scale. Now the biggest takeaway here, the Earth is 4.6 billion years old. That's billion with a B. That's really, really old. But humans didn't show up until very recently. We're this tiny little blip of time in the entire lifespan of the Earth. And in that short amount of time, humans have actually done quite a lot to shape how the Earth looks and to change its overall appearance and the amount of biodiversity that shows up. I'm going to skip this little bit about the layers of the Earth. The two layers that are most important for the rest of this little module is the lithosphere, which is the outermost crust, and the mantle, that's the magma kind of part. If you don't know the layers of the Earth, review through this. All right, so we're going to talk a bit about the theory of plate tectonics and how plates move. So, zoom in here a little bit. All right, so there's what's called convection currents within that mantle, so within the liquid part of the Earth's layers. And just like a Hadley cell moves air around throughout the atmosphere, the convection currents in the mantle circulate heat. And in that process of circulating heat, they pull the plates around the Earth. Now, the continents did not always look like this. Many, many years ago, they were all kind of jumbled together into that large formation called Pangea. And we know that they were all close together based off of the fossil record. So we can find fossils in that southern tip of Africa along with the eastern coast of southern South America that are nearly identical. And the only way for these species to have been able to show up in these two completely different locations is if they were once close together. And so by moving these plates around and moving the continents around, we can form them together. And you notice these kind of pieces just fit together really nicely. So that we know that the continents used to be like that. They also be all close together. But over time, the plates have moved. And the arrows on here are showing the direction of plate movement, kind of in general. Now, the Great Pacific Plate is moving mostly northwest. So that means Hawaii is moving slowly closer towards Japan every single year. Now, it's not a fast movement. It's in the scale of millimeters per year. So that's tiny. But the movement of these plates builds up stress. And when that stress is released, that causes earthquakes. And if that earthquake happens underwater, that causes a tsunami because it displaces the water above it, causing that transfer of energy to create these large waves. All right. We can also have what's called a hot spot. And a hot spot, a classic example, is Hawaii. If we look back at this map, the Hawaiian Islands are in the middle of a plate. They're just floating out there in the middle of the Pacific Plate. Nowhere near a fault zone or nowhere near the edge of a tectonic plate. But they're a volcano. And that's because it's kind of a weak or thinner spot in that particular plate. And that's allowing that magma to rise up through the crust to create this little volcano where it's building up the islands. Now we're going to talk briefly about the three main types of plate boundaries. We have divergent, convergent, and transform. So a divergent plate boundary, divergent, it's dividing. If you think about that popular book or novel, the Divergent series, the main character, she was different from everybody else. She was diverging. She was splitting away from what the norm was. So a divergent plate boundary, they're dividing, they're splitting apart. We have convergent, where two plates are coming together. And oftentimes when they're coming together, one of those plates is going to slip down underneath the other. And in that process, it's going to push the other plate upward. And that's what's happening in this picture. We have one of the plates on the left here, it's pushing underneath the plate on the right, and as these two come together, that actually forces a mountain range to be formed. This is actually how the Himalayan mountain ranges are being formed, and they're growing to this day. Every single year, Mount Everest gets just a touch taller. And then we have transform plate boundaries. Think like the faults near California. They're just sliding next to each other. Right. We can create maps based off of where these fault lines are. And this is a big piece of the AP exam, is being able to read maps and look at a map such as this one and make predictions about where certain events are going to take place. Now, earthquakes, that's kind of this shaded area with this gray. It's also within that ring of fire, so within that purple area. That's where earthquakes take place. So that is typically, looking at this map, that's all along fault lines for the most part. Now there's some spots that are not near a fault line that experience earthquakes, and that's for a variety of other reasons that we're not going to get into right now. But for the most part, the earthquakes happen when two plates are pushing next to each other. So in this particular case, both of them are moving northwest, but one is moving a little bit faster, and that's the Pacific plate. So you have two things moving in the same direction, but one's moving a little bit faster. And what happens is sometimes they get stuck and it can't quite go, and it builds up stress, and then it takes a big jump. So it's building, 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 and then there's a jump. And when that jump happens, that is an earthquake. And that can happen when two plates are coming together. They're pushing against each other, pushing, and then all of a sudden one slides under the other. So based off of the symbols on here, we can see a spreading zone is happening throughout the Atlantic Ocean. So that's actually a really deep part of the ocean because it's spreading apart and we're getting this trench in the middle. We can see the subduction zones where that oceanic plate is slipping underneath the continental plate, and that is causing a lot of the earthquakes along Japan in the eastern part of the Asian continent. We also have what's called the ring of fire, and you should have heard about this in past science classes. This is this phenomena where there's a whole lot of plate boundaries right along the edge of the Pacific Ocean, and the way or the characteristics of those plate boundaries have resulted in a whole lot of volcanoes forming. All right, now I'm going to switch gears briefly here, briefly talk about the rock cycle, because it's important to understand the rock cycle when we're looking at how does soil form. Rock cycle should be a review. It really, really should know this by now. But a few extra bits of details. Thinking about the periodic table of elements, where we got individual types of elements. When you put those elements together in certain combinations, you get chemical compounds. And those compounds are also called minerals when they're in the solid crystalline form. Now, when you have a rock, specific types of rocks are made up of certain combinations of minerals. Sometimes rocks are just pure mineral of one type. Sometimes they're a combination. So when you're using the term rock, you're talking about rocks that are made of minerals, which are made of specific chemical compounds. Now there's three main types of rocks. So we have igneous, metamorphic, and sedimentary rocks. There's a fabulous rock cycle song. If you guys bribe me with enough cookies, I might sing it for you. But essentially what you need to know is that the class of rock, so the type of rock, is really just based off of how it formed. If it was formed from magma, that's an igneous rock. If it was formed from heat and pressure, that's metamorphic. That means it went through some type of change. And if it was formed by erosion and then compression, that's a sedimentary rock. Now they can switch between all three types. And the application of this to environmental science is that weathering and erosion breaks up rocks of all three types into small little particles. And if those small little particles are not compressed and cemented back together to make sedimentary rock, that is forming some of the basis of soil. Now there's other pieces in soil than just rock matter, but that is where a lot of the mineral composition of soil comes from. And that is the end of the module. Let me know what questions you have and I will address them in class.